Hello, this is Roger Hosking, and today we're going to present a radar tutorial which gives some of the basics of how radars work. What is radar? Radar is an acronym for radio detection and ranging. As you may know, electromagnetic waves reflect off objects like light rays reflect off a reflective surface. Radars send out pulse signal and look for a reflected return signal pulse. And you probably also know that radar signals, because they're electromagnetic signals, travel at the speed of light, or 300 kilometers per second. The time it takes for a reflected signal to return back to the antenna is twice the distance divided by the speed of light. The first pulse radars were demonstrated in 1934 by the U.S. Naval Research Labs. In 1935, UK and Germany both began advancing radar technology to detect military targets. But useful radars also need to detect the target location, not just the distance. And advanced radars can detect multiple targets, the speed, the heading, the size, as well as the identity of the target craft and perhaps even the country it's from. Radar pulses are always getting smarter. The first radar pulses were simply a burst of broadband noise generated by a spark gap tube. The receivers listened for this burst of noise and measured the time it took for it to return. This worked, but just barely, because there's a lot of other noise out there and it has a very limited detection range. The next radars transmitted pulses at a certain radio frequency. So the radar receiver would tune only to that frequency and measure the time of the pulse returning at that frequency. It eliminated noise from all the other interfering sources. It improved detection range, but because it's operating at a single frequency, it could be jammed by an enemy jammer that would transmit a powerful signal at that same frequency. Modern radars use complex waveforms called chirp pulses, which sweep from one frequency to another during the pulse, or even do more complicated waveforms within the pulse. The receivers can then correlate the return signals by matching that exact chirp pattern. This is sometimes called a pulse-matched filter, which is quite a complex operation. We'll look at it a little bit later. The benefit here is that the radar is much more difficult to jam. Let's take a look at a radar system that most of you are familiar with, the rotating directional antenna radar. Here, pulses are emitted as the radar dish rotates 360 degrees around on its platform. The antenna receives the return signal from the target. In the radar vector display, a CRT beam is deflected from the center to the edge once for each pulse. The angle of each deflection matches the angle of the radar dish. The return signal intensifies the CRT beam, making a spot that you can see over in the right circled in red. The angle of the target is the angle of the antenna and the display, since they match. And the target distance is measured by the distance from the center of the screen to the spot, which is proportional to the time it takes for the radar pulse to travel to and from the target, and hence proportional to the distance to that target. Radars are always evolving. In the next example, we have a conical scanning radar. Here, an outgoing radar beam rotates in a small circular conical pattern around the main beam axis, instead of just a single beam as we had in the previous radar. The return pulse is highest when the transmit cone angle is centered on that particular target. And as the beam rotates, you'll find you'll get a peak in the response of the return pulse when the position of the beam within that conical pattern is closest to the target or centered on it. This gives you a much better resolution than a single fixed beam in the previous example. The next radar we'll look at is called monopulse radar. It locates a target with a single radar pulse, and it uses a multi-element receive antenna. 3 signals are delivered from the antenna down to the radar processing system. The first is the sigma, or sum signal, that is the summation of all of the 4 different patches. The second is the delta A, which is the delta azimuth, which subtracts A1 minus A2 in signal. And the delta E is the delta elevation, which is E1 minus E2. Those three signals go down to a signal processing engine that calculates the phase shift between the main sigma or sum signal and the delta A signal. That allows you to determine a very accurate azimuth angle of the target. And the phase shift between the sum and the delta E signal determines a very accurate elevation angle. Here the benefits are that there are fewer pulses needed than with a conical scanning radar or the rotating antenna. And this makes the radar system more difficult to detect, or we say it's a quieter radar. And with the additional signal processing, it gives you more target detection accuracy. Radar systems are always getting smarter, thanks to organizations like MIT Lincoln Laboratory. During World War II, MIT Radiation Laboratory was started for radar development for the war effort. It evolved in 1951 to MIT Lincoln Laboratory and still leads the world in radar development. One such radar is Doppler radar. If a target is moving, the return pulse is shifted slightly in frequency. If it's moving away from the antenna, the return pulse is lower in frequency. If it's moving towards the antenna, it returns a higher frequency pulse. Measuring the frequency of shift allows you to compute the velocity and whether or not the target is coming closer or going away from the antenna. DSP has really revolutionized radars. In fact, funding for the first DSPs was mainly driven by radar requirements. The first devices really simplified the intense computations for pulse-matched filters, and allows the use of more complicated pulse waveforms and adaptive pulses to reduce susceptibility to jamming and improve the detectable features of the target, size, shape, and so forth. Most advanced radars use pulse compression. It's an extremely popular DSP algorithm. In pulse compression, you compute the FFT of the outgoing radar pulse, called the reference pulse, to create its spectrum using an FFT block, and you do the same thing for the return radar signal coming back to the antenna. These two spectra are then multiplied together in a complex digital multiplier and then converted from the frequency domain back to the time domain to form the pulse compressed output signal. The result is mathematically equivalent to a very precise convolution function. Effectively, what it does is it reduces the complex radar pulse chirp in the return signal to a single spike in the time domain. In fact, Pentec developed and sold a pulse compression core for Vertex 4 in 2004. Pulse compression can be very useful when you have two targets in your radar field. Here we have a single target which returns a signal after the pulse reflects from the target back to the antenna, arriving at time t1. And here you can see a time waveform of the returned chirp pulse that shows a frequency sweep within the chirp. We have another target that's farther away that returns a signal starting at a later time t2, returning its own chirp from that particular radar signal. Now these two signals are superimposed on top of each other in the return feed that comes down from the antenna to the signal processing system. But if we're using a pulse compression algorithm, what we get at the result is a two-spike display in time, which then tells you precisely where the target 1 is and where target 2 is in time. Again, the wide duration of the chirp pulse is reduced to a single spike in the pulse compression. So you can see why pulse compression is such a useful algorithm for radar. There are many different types of radars, and some are classified by the antenna pattern for each system. A monostatic radar has the transmitter and the receiver in the same location. So here a transmitted signal comes from the antenna to a target, reflects off the target, returns the signal back to the same antenna location. A bistatic radar has a transmitter and receiver in different locations. The transmitted signal reflects off the target and is picked up as a return signal from the other antenna. In a multistatic radar, we have one transmitter and multiple remote receivers. So here we're picking up the return signal from two different antennas. Now, by using two antennas, we're not only able to get the distance to the target, but by triangulation, we can actually do the location of the target as well. And likewise, you can extend this to combinations where you might have the return signal going back to the transmit antenna. Passive radars are becoming increasingly popular. Here, the radar system hijacks a commercial broadcast radio signal like an FM station or a cell phone signal as the transmitted signal. Then using bistatic array, where you have an antenna located remotely from that broadcast station, you can use pulse compression to take the signal that's coming from the transmit tower as your reference pulse and take the signal that's coming from the target reflected back as your return pulse. And thereby, pulse compression can actually separate the signal, the unique signal that's being returned from the target. The nice thing about passive radar is that it's completely quiet and undetectable. It's, after all, a receive-only system. The transmitter is always operating. There's no license required for the transmission. And the multi-static operation allows you to add another antenna or multiple antennas to do triangulation of the return pulses using the same common reference pulse that's coming from, in this case, the FM station. Passive radar is usually better when you have a fixed radar system that's known with a good transmit, good quality, reliable transmit station. Radars operate over an extremely wide range of frequencies. This chart shows you different frequencies for each band of radar, starting at 3 megahertz and going up to over 100 gigahertz. Each of the letters that you see here is associated with a certain range of frequency that's been traditionally assigned through use and application. It shows on the right, notes and application section, the different heritage, if you want, of the different types of radar bands, what they're used for, some of the applications, and some of the benefits of each. So this chart can be very useful if someone asks you about a particular S-band radar or a KU band radar. You can get a little bit more information and reference as to what exactly that means. So this could be a very useful chart to start becoming familiar with the language of radars. Let's take a little closer look at how you generate and acquire radar pulses and then what you do with them. So the relative timing of the outgoing pulses and the reflected radar pulses must be extremely precise. Ultimately, this determines the accuracy of your distance calculation. So imagine we have a radar system and we transmit a pulse P1 which gets sent up to target A and which returns a return pulse at time A1. And let's suppose we have another target B that returns from the same outgoing pulse a signal at time B1. And you can see that, of course, B1 return pulse is later in time because target B is farther away from the antenna. From the math, we know that the travel time from the radar to the target and back again is equal to 2 times the distance divided by c, where c is the speed of light. So the distance is equal t, the travel time, divided by twice the speed of light. So to compute the distance to each target in this example, we first measure the time that it takes for the return pulse from target A at time A1 to come back, and that happens to be 100 microseconds. So using the formula, we plug in 100 microseconds in for the period, divided by twice the speed of light, and we get a distance of 15 kilometers for target A. We can also compute the distance to target B by measuring its return time. The reflected pulse B1 from target B is 200 microseconds. Plugging that into the formula, we get a distance of 30 kilometers to target B. These are the basic principles for doing radar measurements. Let's take a look at one of the problems in radars, and that's called range ambiguity. First of all, we'll introduce the term pulse repetition frequency, or PRF. This is the number of pulses per second emitted from the radar. Another term called PRI, or pulse repetition interval, is the time between each pulse. In fact, these two are measuring the same thing, one in time and one in frequency, and the PRF and the PRI are reciprocals of each other. So you might think that more pulses would give you better tracking of the target. But what happens if we transmit the next pulse too soon after the first pulse? In the example that we showed on the previous page, we had the two returns A1 and B1, but what if we have a second pulse coming out at time P2 going to those same targets? The return signal from target A and target B will appear as A2 and B2 pulses. Now, because of the time that the target takes to reflect its pulse, you may not know exactly which pulse belongs to which target. For example, is A2 pulse really from target A, or could it be from target B? And that is the essence of range ambiguity, which return pulse belongs to which target. And in this case, you're not really sure of who caused the return signals on A2, B1, and B2 signals. So how can we resolve the range ambiguity problem? One of the ways is to increase the spacing between the outgoing pulses, as we see here. Now what you can see is that the return signals from pulse 2, which are A2 and B2, are now moved out beyond the time where we're looking at the signals coming back from pulse 1, which are A1 and B1. This eliminates the overlapping of the return signals so that the pulses that are received are clearly due to a single outgoing pulse and not returning on top of each other. What you can do is to establish a range gate which defines a start and stop time for collecting data relative to each outgoing pulse. So range gate 1 is set up to only look during the time that signals can come back from pulse 1. And likewise, you can set up another range gate from pulse 2, which will only allow capturing of return pulses during the time that you can expect a reflection from pulse 2, shown here as A2 and B2. These range gates have been used for many years. It's relatively simple circuitry, and it gives you a lot of flexibility in tracking targets because you can adjust the PRF and you can adjust the range gates according to different acquisition scenarios for different types of targets and applications. Let's look at another more advanced way to resolve range ambiguity, taking advantage of some of the modern signal processing that we have in DSP methods for radars. What if every outgoing pulse was different and unique? So we have P1 going out, we have two reflected signals coming back as A1 and B1. But what if the second pulse was completely different in character, a different chirp pattern from the first pulse? Its reflected return patterns would also be unique and different from the first return pulse. And likewise, we have a third pulse returning yet a different pattern, and perhaps a fourth pulse returning a different pattern yet. So now what we're going to do is use our pulse match filtering and pulse compression methods to separate these pulses, even though they are interleaved in time and otherwise very difficult to separate. In pulse match filtering, each returned pulse is matched up uniquely with the character of its outgoing pulse. And so you will get a unique spike for each of the outgoing signals. There's no overlap problem, even though they are mixed in time and mixed in order. This does require very sophisticated waveform generator for the outgoing pulse. Remember, each one is different. And it requires the digital signal processing of pulse compression in order to untangle these mixed pulses that are all appearing in sequence in the return signal. The benefits here is that you can support much higher PRFs, so you can do faster tracking, and it also eases some of the limitations of the more primitive range gate architectures. Radar technology is always evolving, As we've seen, we can do very complicated things like have a different outgoing pulse waveform for each radar pulse. We can set the power levels. We can have different antenna configurations. As we've seen, we can do different PRF, PRI, and range gates and so forth. In fact, there are a lot of different types of radars, each addressing a particular application. So you can have a search radar, a target acquisition radar, target tracking, missile guidance. There's many, many different operational modes. But each of these modes can take advantage of new technology for FPGAs, DSPs, A to Ds and D to A converters, digital up converters and down converters. And you can also have these different devices adapt to changing conditions so you can do a better job of tracking. And with the programmability of these features and with digital signal processing, you can track targets and adjust the parameters to give you the best target tracking operation for a particular application. There's also major worldwide spending on upgrading radars. As each new radar comes out, there's a countermeasure that tries to defeat it. And so radar technology is constantly being funded, and it's always evolving, and it's always taking advantage of the latest technologies. How do you generate waveforms with Pentec products? Pentec products include DMA controllers and waveform generators that are standard features in the IP for the FPGAs on our Cobalt, Onyx, and Flexor product lines. To start with, the user places a custom pulse waveform in system memory. This would be a table of digital samples. We then use the PCI interface to access that memory from a DMA linked list controller, which is part of our board, to fetch the waveform table. We then send that waveform, which is a series of digital samples, to an onboard memory, or we actually send it to a waveform generator engine directly. We can go either way, to memory or directly to the waveform generator engine. Then what the customer does is fill out a waveform generator linked list. This is a list that's accessible from system memory, where the customer can specify which waveform he wants, the triggering modes, the number of repeat cycles, delay information, and so forth. This gives you a very automated, precisely timed, complex radar pulse generation system that's extremely powerful. Let's take a look at how the pulse waveform generation engine and the linked list really work. Suppose you have different waveforms loaded in memory, and this could be either system memory or local memory. Each of these waveforms represents a different pulse pattern or a different chirp, for example. In the waveform generation linked list, we have one link for each waveform scenario. Link 1 points to memory location 36, which specifies the location of the samples for waveform that's associated with link 1. We also can specify the delay after trigger, the length of the waveform, the number of repeat cycles, and then the next link. So in each of these link descriptors, we have a complete script for how the link is played. The second link points to a different waveform with its own parameters, the third to a third waveform, and the fourth link to a fourth waveform, each of them representing a different pulse, for example. Now, let's say we start by saying, I want to start with link number 1. I get a trigger. And what the engine does is it uses the parameters in the link to generate this waveform after a delay of 7 clock cycles with a length of 24 samples and a repeat cycle of 3 times, and it completes the output generation. Here that waveform appears at the D to A converter output as an analog waveform. Now at the end, we see the next link is link number 3. So on the next trigger, we start generating the waveform associated with link 3. Here, we fetch the waveform after a delay of 9, a length of 4, and 5 repeat cycles, and we see the next link is 4. We jump to link 4. We have yet a different waveform. We repeat it 9 times with delay of 5, a length of 5, and then we jump to link number 2 for our last waveform in this example, generating a waveform with a repeat of 2 cycles after a delay of 15. So the nice thing about this linked list is it can contain up to 64 different links, each one associated with a different waveform and a different set of parameters to describe how it's played. You can see how flexible this waveform linked list is because it can give you a lot of freedom in terms of assigning different types of waveforms with different characteristics to each of the pulses that are generated out, precisely controlled by the trigger. So you can cover a lot of different applications. Of course, the other side of radar is acquisition of the radar pulses. Pentec incorporates DMA controllers and data acquisition engines in all of its IP for Cobalt, Onyx, and Flexor A-to-D products. And we use a similar linked list for the AD acquisition, very similar to the linked list that we used for the generation in the previous slides. So we specify the capture length, the delay from trigger, the destination for memory, and then the number of times we might repeat, the triggering mode, and so forth. So in this case, what we're doing is we're sampling data with the A-to-D converter shown down at the bottom left, using the acquisition engine driven by the parameters fetched from the acquisition linked list table. Once the data is captured, the DMA controller also uses a linked list table to specify the location of where it puts the captured data block to system memory, and this is transferred across PCI Express into system memory. Each block contains metadata that includes timestamping and an ID header to uniquely identify each captured block of data. It also delivers an interrupt to the system processor to notify the processor that the data is ready for processing. This can give you a very nicely automated, precisely timed range gate for radar pulse capture. Let's take a look at how the acquisition linked list range gate engine works. We start out with the acquisition linked list table, which is filled out by the customer specifying the delay from trigger before the acquisition begins, and then the length of samples of the acquisition itself. These are the two parameters that are needed to specify a range gate that we've talked about before. We can also specify the number of repeat cycles if that's required. And we also specify, of course, the link number. We can tell the system whether or not to wait for a trigger or not, and then what to do for the next link. And like the waveform generation table, the acquisition linked list table also has 64 entries to have 64 different types of range gates automatically sequenced according to the next links that you put in. When data is collected in the acquisition engine, it can be delivered to local memory where it's stored in DRAM, for example, and then finally delivered across PCI Express to a system memory destination specified by the DMA controller. Along with the data, we also deliver metadata in the form of header information that describes the data samples themselves. Metadata contains the timestamp and data capture information. We have a lot of hardware counters, real-time clocks, and so forth in the engine, and those values are constantly updating as time goes on. We capture, at the time of a trigger, the values of each of those counters and preserve that information, including the PPS, or the pulse per second count, the offset in terms of number of clock cycles since the last PPS, the trigger number, and so forth. We preserve this information and send it out with the data delivered to system memory. The system memory then has not only data samples, which are sent out as a group of digital samples, but also a packet that goes in front of or adjacent to the data packet that contains this metadata, so that every time we get a trigger, we capture a new set of values and append it to the data packet itself. This is an extremely useful way for keeping track of exactly where each acquisition block occurred in time and in sequence. Pentec products are truly geared for radar. Our software radio products are filled with critical features very important to radar operation. We include the FPGAs and DSPs for advanced signal processing tasks like pulse compression, for example. We also include A to Ds and D to A converters for digitizing and generating the pulses. Inside the FPGA, we include our waveform generation engines and our data acquisition engines, along with the link-list controllers. We include digital up converters and digital down converters for interfacing to IF or RF ports on your system. We spend a lot of effort in making sure that all of our products have synchronous operation across multiple channels and multiple boards. This is very important for phased array applications. We support our products with powerful development tools, both for the FPGA and for C language programming. Our products are available in all popular form factors for embedded systems, including VPX, XMC, Compact PCI, VME, PCI Express, Advanced TCA. We also offer diverse environments for our products with levels of ruggedization that allow them to work in embedded military applications in very severe environments with both air and conduction cooling models available. We also provide recording and playback systems. These are complete instruments that can be used for testing your radar system, both for acquiring radar pulses and also for generating radar pulses. Our factory has excellent support engineers that are available at no extra cost for life, available to you to help you get your application up and running as quickly as possible. For more information about our products, please visit our website at pentech.com. Here you'll find our product selectors to help you locate the exact product to meet your needs based on the parameters. You'll also find a series of handbooks that gives you the background theory of how our products work and also some examples of applications. Here you'll also find tutorials, data sheets, specifications, product manuals, articles, videos, and newsletters, all of which you can download to review at your leisure. Please feel free to contact us by phone or drop us an email. Again, thank you for attending today, and I hope you found the information useful.